Mechanics of Materials, Chapter 9, Stress Transformation. Let's solve another problem in stress transformation. So in this example, we have a sample handling a shear and normal stresses in these planes, and we want to know what's the state of stresses if we just rotate this element by a 30-degree like clockwise rotation. So if we have a theta like 30 degrees clockwise, we want to know what is the state of stresses on that piece of element. So what are the stresses if we just rotate our sample like theta like 30-degree clockwise, which is a 1930 degrees, because it just moves down in coordinates. So we have a, if we just use the formula sigma x prime, which is, this is our x prime, and that's a sigma x plus sigma y over 2 plus a summation of the stresses. This is a push, that's a negative 80, that's a pull positive 50 over 2 plus sigma x minus sigma 1, sigma x minus sigma 1 over 2 cosine of 2 theta, and theta is 90 negative 30 degrees plus a negative 25. If you remember in the formula, tau, which is like in a positive y direction, is a positive tau, so we have a 25 but a negative because that's a downward a shear stress, and times sine of 2 times negative 30 degrees. If you add it, it just gives you a sigma x prime is a negative 25.8 megapascal. Likewise, if we want to know what is the state of stress for y prime axis, sigma y prime is a summation of those two minus, if you subtract them, time cosine of 2 theta, and then minus tau xy sine of 2 theta. If you just replace the numeric value, it just gives you a sigma y prime, a negative 4.15 megapascal. And the final one is the formula for tau x prime y prime, which is using this formula, placing the new value, negative 80, negative 50 over 2 sine of a negative 60 plus a negative 25 cosine of 2 negative 60, 2 negative 30. And it just gives you negative 68 for tau x prime y prime, a negative 68.8 megapascal. So that's the state of stresses like sigma x prime, sigma y prime, tau x prime, y prime in the brand new form, which is moving from x, y axis to x prime, y prime. These are the state of stresses after a negative 30 degrees in plane rotation, which translates like two-wise rotation in Mohr circle. We can also solve this problem in a second approach, which is a Mohr circle approach. So if we just draw our Mohr circle, so if you look at this x element here, there is a push, so a negative 80, and there is a shear stress, and that shear stress, if you remember the convention of Mohr circle, it just says if your shearing stress wants to rotate your element like clockwise, the point goes up in above in x-axis. So that's our x, that's the top of tau and sigma axis, and that's a negative 80 normal, which is a push, and a positive 25 base of our convention. And that's a translation of this plane on Morse circle, and that's a plane A, this dot. Let's see what's the story about the other plane, which is a positive 50, and that's a of 50. And if you look at the top of the element, this kind of shear, it just tries to turns your sample like counterclockwise. So if that's the case in tau sigma base of convention, a counterclockwise takes you down below the x-axis in Morse circle. So that's a negative 25, just come from this convention. And we just translate this plane also like a dot in Morse circle by a specification of 50 and negative 25. So we have 2 points, we can draw our circle. So this is our center, which our diameter passing through. And if we just consider this point like origin, very first step is, let's say, alpha. We can call this angle by like alpha, and that's arctangent of 25, which is shear over 65. So we can verify later on this distance is 16, and that's sigma average. And then this is negative 80, so a 15 plus 65 makes it a 80 in negative x direction, and that gives us the alpha is 21 degrees. So if we want to have a rotation like 30 degrees, clockwise, so it just turns like this and translate like 2y's doubled in the circle. So it just takes us from x to 1x prime like here. And if this is 21, this is 60, total of this angle is 90, so it just remains a small angle like 9 degrees for us. So let's put it this way. Let me make it cleaner. So this is 21, 60, make it like 81, and total of 90 degrees is, it just gives us this small phi over 9 degrees. That just gives us this 5, it's 9 degrees. And also we do know from the Morse circle, that's r, the radius is a square root of sigma x minus sigma y over 2 parentheses square plus tau xy squared. If you place the numeric value for that, it just gives us a r of 69.64 megapascal. And this small horizontal distance at the top here, that's r. This is our r sine of theta, r sine of theta. So that's r sine of theta, and sigma x prime is negative 15, which is here. Sigma x from our origin is negative 15 minus, it just moves a bit more to the left, and that's a r times sine of 9 degrees. That's a negative because we just move a bit more in negative direction of x, and it just gives us a negative 25.89 megapascal, which is exactly the same amount from the formula. Likewise, if we just want to know what is our how x prime y prime is, that's this horizontal amount. It's just a bit below r because we are not, it's not a fully developed r here yet. So we are somewhere like here. So the vertical distance is just a bit off than the total radius, and that's r by cosine of theta. Theta is 9 degrees. They are, because the angle of theta is pretty small, r cosine of theta, which is this yellow line, it's almost very close to the radius itself, and that's, if you put it on the like mass, it just gives you 68.78 megapascal, which is again like very close to the first answer. So if you want to make a comparison between formula and Mohr circle, so these are the two formula, like sigma x prime, tau x prime, y prime. Numeric value for them is sigma x prime a negative 25.8 megapascal and tau x prime y prime a negative 68.8 megapascal. And if you just verify the our result from the Mohr circle, it just gives us a negative sigma x prime is a negative 5.89, almost the same, and tau x prime y prime 78, and they are pretty close enough to solve the problem from the same approach. In next problem, we're just calculating the, for the same problem, we'll calculate the principals and also principal planes. Thank you.